Downtime. All right, we are recording this. So I am Ashley Simone. I am the chair here. It's the Los Angeles Metropolitan Mass Spec Discussion Group. Welcome to our first inaugural virtual series. We are hoping to do one of these a quarter with a different area of focus. So if you got our email, you might have seen that. The area of focus for this particular talk is mass spectrometry as used in environmental chemistry. So I have two illustrious guests with me today. I'm really excited. So we're going to hear today from Professor Dan McCurry at USC, and then followed by Dr. Mark Strynar from the US EPA, joining us from the East Coast, which is amazing. So I'm going to go ahead and introduce Dan first. The format of this will just be Dan is going to give a around 25-minute talk. We'll have 5 minutes for questions, so please save your questions for the end, or you can drop them in the chat. And then followed by Dan, we'll have Mark give his presentation, again, another 25-minute presentation, followed by questions, and then we'll call it a night. So tell you a little bit about Dr. Daniel McCurry. He is an assistant professor of civil and environmental engineering at the University of Southern California. He completed his PhD in civil and environmental engineering with a chemistry minor at Stanford in 2016. Prior to Stanford, Dan earned a master's in environmental engineering from Yale and a bachelor's in civil engineering from the University of Cincinnati. He worked in the US EPA Office of Research and Development. Dr. Dan McCurry's research focuses on protecting public health by improving the long-term safety of engineered water sources. He applies the tools of organic and analytical chemistry to water quality challenges related to disinfection of wastewater and drinking water, with particular emphasis on identifying formation mechanisms and precursors of disinfection byproducts to facilitate their prevention. So welcome, Dan. I will hand the mic over to you.
Sounds good. I wouldn't have sent you such a long bio if I knew you were going to read the whole thing. Now I'm embarrassed. Anyway, give you just 2 seconds to put this on presenter view and then use the trick that Mark told me. Actually, Dimitri, are we good? Are you seeing the full screen right now?
We're good now.
Okay, perfect. All right. So as I told Dimitri and Ashley when they invited me to do this, this talk is perhaps maybe a bit more applied than people in this group might be used to seeing. It's not really so much about mass spec itself. It's more about an application of mass spec. I did include exactly one slide that's explicitly on a mass spec technique that we had to develop. But for everything else, rest assured, every data point was collected on a mass spec. So hopefully it satisfies conditions for this organization. So anyways, Ashley mentioned I work a lot on water. And my research on water is especially motivated by water scarcity. So if you live here in LA, which I see most of you do, you may or may not know that the vast majority of our water is imported. We can only get about 10% of it locally, and the imported water comes from hundreds of miles away through this complicated system of aqueducts bringing us water from the Sierras and the Colorado River. And that engineered water infrastructure has worked out for us for decades, but it has a couple of vulnerabilities. One of the big one is that it relies in large part on snow melt. So if you look in the middle there, those are satellite images of the Sierra Nevada mountains, and the melting snow in those mountains supplies the aqueducts on the left-hand side of the screen that come from Northern California. And so in recent years, last year was a big exception, but we've been getting more and more snow droughts where little snow compared to historical averages falls in the Sierras, and we might not be too far away from our first zero snow year. And so in response to this kind of threat to our water security, California, along with many other states, is rapidly expanding water reuse, meaning recycling domestic wastewater as a water source. So that map on the right shows planned or permitting for water reuse projects in California. So my overall goal in research, and I probably do 75% of my research on wastewater recycling these days, is to make wastewater that's recycled so safe that it's maybe even safer than conventional tap water. And the specific projects under that umbrella kind of take two flavors. One is really about identifying potential chemical threats and figuring out how they're formed or transformed in reused processes. And the second one is about maybe developing new treatment technology to address those problems. So I'll mostly be talking about the first case today. And specifically, I'll be talking about a class of chemical contaminants in recycled wastewater So wastewater, as you might expect, contains thousands of chemicals. And so it's worth a little bit of our time stepping back and thinking about which contaminants are really worth worrying about. And so about 10 years ago, the National Research Council, which is part of the National Academies, put together this huge water reuse report. And as part of it, they did a risk assessment on chemical contaminants in recycled water. And now the output of this risk assessment they expressed as a margin of safety, which to engineers is a very familiar concept. But since most of you are chemists, I'll just briefly explain that essentially a big number is good. So the margin of safety is essentially concentration at which we might be concerned divided by concentration at which this chemical actually appears in the environment. And so anyway, among all the contaminants that were considered in recycled wastewater, the pharmaceuticals that sometimes grab headlines had huge margins of safety, meaning that their concentrations are far, far below where they threaten human health. In contrast, disinfection byproducts, which are chemicals that form as an unfortunate consequence of chemical disinfection, rated kind of highest in terms of concern, meaning their numbers for these margins of safety were lowest. And so just a few years ago, study that tried to inventory the final chemical composition of recycled wastewater after all these expensive treatment processes found that about 6% of the dissolved organic carbon, meaning the total sum of every organic chemical in this product water, was disinfection byproducts. And another study recently figured out that the concentrations of disinfection byproducts at utilities that supply both recycled and conventional water were comparable. So this is kind of surprising information for people in my business because we tend to assume that we're so good at recycling water that the product water is basically what comes out of your Millique machine. But it turns out there's some things we might be concerned about. And so among these disinfection byproducts, we can split it up even further. So there's been about 700 disinfection byproducts identified to date, mostly in normal tap water, and 11 of which are currently regulated by the US EPA in drinking water. But it turns out that among these 700, they vary vastly in terms of their toxicity. And so toxicologists have started to tell us some things about which ones we might be most concerned about. And so it turns out that these small molecule disinfection byproducts differ vastly in toxicity depending on whether they do or don't contain a nitrogen atom somewhere in their structure. I'm not a toxicologist, so I'm not prepared to explain the origin of that phenomenon, but it just appears to be true. And on the right-hand side, if you compare different classes of disinfection byproduct molecules that have been frequently detected, the two that are underlined, so halomethanes and haloacetic acids, those are the two main classes that are regulated right now, and they're among the least toxic that we're aware of on a combined genotoxicity or cytotoxicity basis. In contrast, some of these nitrogenous compounds that are towards the bottom of that plot are among the most toxic. And the one I'll focus on today is this class of compounds called halonitromethanes, including chloropicrin, which is the structure depicted there, which is kind of the poster child for this chemical class. And is a chemical we've known about for a long time. It was used as a chemical weapon in World War I and occasionally as an agricultural fumigant. And so these halonitromethanes, because they're so toxic and fairly widely detected in drinking water, they're on the EPA's candidate contaminant list 5. If you're not super familiar with how the EPA regulates chemicals in drinking water, Mark could tell me this, I forget, I think it's 6 years, 7 years, something like that. The EPA comes up with a list of chemicals that are candidates for possible regulation. And 3 of these halonitromethanes, including chloropicrin, are on there. So anyway, around the end of my PhD, I started to get interested in how do these compounds form during water disinfection. At the time, I was just working on ordinary tap water treatment, and since coming to USC, I've shifted gears into wastewater recycling. So anyway, I started digging around in the literature to figure out what we know already about halonitromethane, or specifically chloropicrin formation during water treatment. And so we have a few different chemical disinfectants that we use for water treatment. In this country, chlorine is the most common by far, but in other parts of the world, there are other choices, maybe a bit more common, like in some parts of Europe, they tend to use ozone. And so this nice paper from Switzerland in the late 80s figured out that chloropicrin formation in drinking water was associated with the sequence of ozone followed by chlorine. So on that plot in the top left, you have a variable ozone dose followed by a fixed chlorine dose, leading to increased chloropicrin formation, versus if you switch the order, you don't get anything. So that tells us that some kind of mystery precursor is being ozonated to some kind of mystery intermediate, which then gets chlorinated to chloropicrin. And this is potentially a troublesome finding for water reuse because in many water reuse treatment configurations, and I'll go through later what all these different treatment steps are as they become more important, but the main thing to point out here is these are two different options for treatment trains recycling wastewater, and they both contain ozone as the initial disinfection step. And then they'll typically be followed at the very end by chlorine as the final disinfection step because chlorine tends to persist longer. And so you can leave it as a residual disinfectant in the pipes to prevent reinfection and things like that. So we know ozone followed by chlorine is responsible for this highly toxic byproduct that might be regulated. And then I started to dig a little bit deeper to try to figure out where it might come from. So I took a peek in the organic chemistry literature, and there's this really nice paper, single author paper actually, in JAX from 1980, where this guy, John Orvik, working at Dow, figured out that if you want to make chloropicrin at really high yield, a good way to do it is to start with nitromethane, that compound in the top center there. It turns out if you take nitromethane, you can chlorinate it to chloropicrin at 100% yield. So that's obviously a synthetically useful reaction, but was exciting to me too, because in the world of disinfection byproduct chemistry, we tend to be down in the sub 1% yield territory when we're trying to explain formation of byproduct X from precursor Y. The chemistry of this reaction is pretty interesting to me because if you look at the structure of nitromethane, it doesn't look very oxidizable. You know, there's no carbon-carbon double bonds or reduced nitrogen or anything like that. So what actually happens is because nitromethane is a fairly strong carbon acid, it can deprotonate to form this nitromethyl anion, which has a nice electron-rich lone pair that can be attacked by chlorine in a fairly rapid step to form chloronitromethane. And now, if you remember your physical organic chemistry class, addition of that extra chlorine is going to further decrease the pKa of that compound. So since it's more acidic, it's going to deprotonate even faster. So it loses another proton, gets chlorinated quickly again, and it's kind of this accelerating cascade of deprotonation followed by chlorination, ultimately leading to chloropicrin. So this is cool, but it doesn't quite tell us where chloropicrin is coming from in recycled water because it doesn't include an ozone step. And as I said, these Swiss people back in the 80s figured out that it was ozone followed by chlorine that really explained formation of this toxic compound. The other thing that was a little bit of a head scratcher is nitro compounds don't really appear in nature. You know, if you crack open a biochemistry textbook, you're highly unlikely to find a natural product or biomolecule with a nitro group hanging off of it. So clearly something is missing. And around when I started at USC, some collaborators in Switzerland published a very nice study where they found that if you ozonate aliphatic amines, you can convert them, and this is under mild conditions in water, to nitro compounds at about 100% yield in some cases, sometimes less, but pretty good yields. Excuse me. So that's potentially exciting, but still doesn't quite fill in all the gaps for us, because if you ozonate a generic primary amine, let's say, you'll make a generic nitroalkane rather than nitromethane, which is this you know, sort of magic precursor that we suspect might be a key intermediate for this chemistry. So then I dug a little bit more into some old organic chemistry literature and found actually back in the 60s and 70s, this guy Philip Bailey at Texas in Austin was ozonating lots of amines under different conditions, you know, in organic solvents and extreme temperatures and so on, but nonetheless found that you could ozonate not just primary amines, but also secondary amines to make nitro compounds. And I'm not sure if you can see the mouse if I use it as a cursor, but what he reported is that if you ozonate a secondary amine, on the way to a nitro compound, you know, maybe this seems obvious in retrospect, but you have to go through a dealkylation step where you kick out either this R1 or R2 alkyl group to form either the R1 or R2 nitroso compound en route to one of these two nitro compounds, the R1 or R2 nitro compound. So our sort of like aha moment or insight or whatever when I first started at USC was realizing if we constrain this a little bit more and specify that instead of just a generic secondary amine, if we start talking about secondary N-methylamines, where we've replaced a generic R group with a methyl group, a CH3 right here, then we should have on average maybe a 50-50 chance of making nitromethane as opposed to generic nitro compound. So the pieces are starting to come together here. If we can figure out some kind of secondary N-methylamine that's prevalent in wastewater, then we would expect ozonation of that compound would form nitromethane very efficiently, and then chlorination of that nitromethane might explain the chloropicrin that we see in practice. And so again, around my second year at USC, I started thinking about like what kind of secondary N-methylamine compound might we find in wastewater. And so I was reading all kinds of literature about inventories of contaminants in wastewater. And I finally came across a candidate that I was a little bit excited about, and it was drugs. So it turns out that many of the central nervous system stimulants that are consumed by humans all share this common secondary N-methylamine functional group. And these are things ranging from the innocent or even endogenous, like adrenaline, to the maybe not so innocent, like methamphetamine. And so we hypothesized that those things could be ozonated, make it to nitromethane, and then it's not too hard to turn those into chloropicrin, which again is the toxic, potentially regulated byproduct whose formation we're trying to explain. And conveniently, all of these drugs have been measured in wastewater before. Long before anybody ever heard of wastewater-based epidemiology for COVID monitoring, more like 10, 12, 15 years ago, people were doing wastewater monitoring for drugs and basically trying to estimate prevalence of use of different kind of drugs at a population scale by measuring them in the sewer. And so a lot of these papers are pretty fun to read. They'll do things like monitor the sewage of a French town before, during, and after a music festival and see a huge cocaine spike on Friday and Saturday, things like that. But the point for us is that all of these chemicals in the top of this ChemDraw have previously been documented to exist in sewage. And so we wanted to test if we ozonate these things, do they turn into nitromethane at reasonable yield or not? But there were a couple challenges. The first of which was methods. And so I mentioned at the beginning, this is really an applications talk, but I have exactly one slide on mass spec methods. So in the past, we're not the first people to ever try to measure nitromethane, but it's a pretty challenging analyte. It's very polar, it's very low molecular weight, you can't extract it very well. And the best method in the literature that had been reported had a detection limit around 10 parts per billion, which sounds low, but really wasn't good enough for us. So we bought a GC triple quad with a static headspace sampler, so not SPME or Persian trap, just static headspace sampling, which allowed us to overcome this, poor extraction efficiency of nitromethane. If you try to extract it into MTBE or whatever your favorite solvent is, it almost doesn't work at all. And so we were able to get our detection limit down to about 0.1 or 0.07 ppb, which was good enough for our purposes. So the next challenge is we wanted to buy all these chemicals and ozonate them and see if they made nitromethane. Some of these you can just ring up Sigma and buy no problem. Others require a conversation with the government. Maybe some of you, if you're working in MedChem, have had this conversation before. So the DEA made us buy an 800-pound safe and get background checks and all that stuff to be able to store a hilariously small vial of methamphetamine in our lab. Anyway, we went through all that, ozonated these chemicals, and it turns out they all made nitromethane. These are the 10 that we tested, and the molar yield ranges quite a bit, and we did some mechanistic work to try to explain that I'll spare you of today. But the point being is that many of them produce nitromethane at pretty appreciable yields. So then we started to wonder, okay, if we know that these chemicals are in the sewer and we know that we can turn them into nitromethane in the lab, if we ozonate real wastewater, does that make nitromethane? And so then we went and just grabbed up a bunch of effluent from wastewater treatment plants around Southern California, subjected them to a range of ozone doses, and sure enough, they all made nitromethane. These concentrations on the y-axis might seem kind of small, but in a disinfection byproduct context, those are actually pretty large concentrations. So then now we know that you can make nitromethane in wastewater, but that still doesn't tell us if it's really this key intermediate towards chloropicrin, the toxic byproduct we actually care about, or not. So to do this, we cracked open the analytical chemistry textbook, trying to figure out how do you explain some certain trace compound really is the precursor explaining formation of some product. And so we ended up doing this with a standard addition assay. And in case you haven't encountered this kind of thing in class or research before, basically, if you want to explain how much formation is attributable to some precursor in a mixture of many different compounds, what you can do is take your sample, which is this first blue dot here with the dotted lines going through it, measure the concentration of that precursor, nitromethane in our case, and then you can spike in a range of supplemental concentrations of that precursor, nitromethane again in our case, apply whatever treatment you want, which for us is chlorination, and then measure formation of the product you're interested in, which is chloropicrin in our case. Then you can draw a line, hopefully it's a straight line through those points, and that allows you to extrapolate back to the y-intercept, telling you how much chloropicrin you would have expected in the absence of that precursor. And then the difference between that and how much you found in the real sample allows you to make an attribution number. And so again, we did this with 3 different wastewaters in Southern California. Without explaining every single detail of these plots, I'll just summarize it by saying that most of the chloropicrin in this wastewater ended up being explainable by nitromethane. So it seems like our hypothesis here is more or less confirmed, that secondary amines in wastewater get ozonated to nitromethane, and then that explains the chloropicrin formation during subsequent chlorination. So this was a potentially disturbing finding for the water reuse business because, like I said, several different water reuse plant configurations that are in full-scale use right now, these are actual plants you could go visit, use ozone as their primary disinfectant, and then will often use chlorine as a secondary disinfectant. So the question is, after the ozone step, do all these other treatment steps that, again, I'll walk through in a moment, so don't worry about these little acronyms on the cartoon, do they do anything to remove nitromethane, or might it just sail through these treatment steps? And again, these treatment steps are designed to remove almost any chemical you can think of. Like in the water reuse business, it's commonly said that the final product water is basically DI water. But we wanted to sort of probe that a little bit and first figure out, does ozonation of wastewater at realistic doses at actual wastewater reuse plants make nitromethane? Because our previous findings were just at the bench scale in the lab. Second, does it get through reverse osmosis, which is the first of those acronyms I was going to explain, this very tight membrane here, and a UV advanced oxidation process, which is a kind of self-congratulatory term in the water business for essentially splitting a radical precursor with UV light to make highly reactive radical species that are supposed to chew up any products getting through reverse osmosis. And finally, if nitromethane does persist through these treatment techniques, do we actually see it turn into chloropicrin during subsequent secondary disinfection? And so we went and sampled basically every water reuse plant that would let us in. And what we found is that in each case, the nitromethane concentration, which is the blue bar, shoots way up after ozonation as compared to the influent concentration. The influent concentration, meaning the amount basically in the sewer, wasn't 0, which was a bit of a surprise. I don't think anybody's really pouring nitromethane down the drain. The best thing we can figure is that nitromethane is sometimes used as a fuel additive during drag racing, and there are a couple drag racing strips in Southern California, it turns out. So maybe it's leaking down somebody's garage drain. So second question is, does it get through these very expensive treatment processes we apply to, again, turn water that used to be in the sewer into essentially DI water that we can drink? And so we profiled the concentration across each of these steps in a bunch of different plants. We found that in many cases it appeared to just sail through. So these bars indicate the concentration after each of these steps: ozone, microfiltration, which just removes particles; reverse osmosis, which is supposed to take out almost anything that's dissolved; that UV radical generation step I mentioned, and then the final product water. And that was fairly repeatable across several different plants that we sampled, where the final concentration of nitromethane remained relatively high. So we wanted to explain this a little bit, see if we could understand this phenomenon, because again, these treatment processes are supposed to remove almost everything from water. So we did some bench scale experiments on both reverse osmosis and UV advanced oxidation processes. Beginning with reverse osmosis, we just fed nitromethane solutions into reverse osmosis membranes at the bench scale and found rejection rates consistently, similar to what we see at full-scale plants, kind of ruling out that it's just like an old leaky membrane or something like that at the real plant. In retrospect, this isn't a huge shock because the secret formula for a chemical getting through reverse osmosis is being small, polar, and uncharged, and nitromethane is all 3 of those things. Then for the next bit about the UV advanced oxidation process, which the chemistry of that looks like this little reaction here. You feed in hydrogen peroxide, split it with 254 nanometer light, and that makes 2 hydroxyl radicals, which are meant to basically rip apart any molecule that's gotten that far in the process. And so there's kind of 2 components to this treatment step. One is just direct photolysis by UV. Anything that absorbs light at 254 might just break down through that mechanism. But what we found, at least at pH 7, which is the green line here, is that nitromethane is a really poor chromophore at 254 nanometers. So that explains why there's not much direct photolysis. If just for fun, you crank up the pH to 12 to turn it into this anion, a nice absorbance peak does show up, but of course we don't run water treatment at pH 12. The second thing we wanted to explain that was a bit more surprising was why the hydroxyl radical formed during advanced oxidation processes didn't do much, because again, that's supposed to tear apart basically everything. And so we did some competition kinetics to figure out the rate constant between nitromethane and its conjugate base anion with this hydroxyl radical. I realize these are busy, but each of these is just the decay rate of some probe with a known rate constant versus the decay rate of our compound of interest. And we found that the reaction rate constants were pretty low for both nitromethane and nitromethyl anion. These actually seem like very fast rate constants if you're used to working in chemical kinetics. But for context, 1,4-dioxane is a wastewater contaminant used as the benchmark in California for these processes, and its rate constant is quite a bit higher. And so pretty much that explains why hydroxyl radical formed during UVAOP doesn't really seem to do much. It's just nitromethane is fairly poorly reactive with it. So then anyway, I can see that I'm running out of time, so I'm going to get right to the sort of last question. So if nitromethane really does sail through these, again, fairly expensive treatment processes we use for turning wastewater into drinking water, does it then get converted into the toxic byproduct chloropicrin that we're concerned about all along? And so we went and sampled a few plants that actually did do this subsequent secondary chlorination with, or secondary disinfection with chlorine after the ozone and a couple other steps, and found that the red bar here, which is nitromethane, gets converted to the blue and green bars, which are chloronitromethane and chloropicrin after the chlorine step that occurs right upstream of RO to prevent biofouling. So with all that being said, does that mean that ozone-based wastewater reuse, especially direct potable reuse, if the water goes straight to your tap as opposed to filling up a reservoir first, is it doomed? Turns out, thankfully, no. So one treatment process I haven't really talked about yet is biological activated carbon. And sorry again for the acronyms. I'm used to talking to engineers. I should have spelled more of those out. But anyway, this is a step that's commonly employed after ozone, where you take essentially a big Brita filter, which is what an activated carbon column is, and you just let it get kind of old and let some bacteria grow on it. And if you feed that wastewater that's been ozonated, it turns out the ozone tends to chop up some of these organic chemicals in the wastewater into bite-sized pieces that the bacteria can then munch on. And so we saw pretty good removal by the biological activated carbon step at every plant that employed it. So anyway, to wrap all this up, I think almost exactly on time, although I guess we started a few minutes late. Wastewater ozonation pretty much always forms nitromethane as a reasonably high concentration byproduct, which can then do a pretty good job of sneaking through all of the sophisticated treatment processes we use for wastewater recycling, and then at the end can get turned into potentially toxic halonitromethane compounds. But thankfully, biological activated carbon seems to pretty drastically minimize that. So the takeaway for me, if you're designing a wastewater reuse plant, is if you're going to use ozone as the main disinfectant, you would be foolish not to use biological activated carbon after it, because it's very cheap and does a good job for removing many contaminants. Anyway, it's exactly 5. So I'll wrap up now by thanking my group at USC, especially Lily Shee, the one with the kind of referee shirt on there, who did most of the experiments talked about today. A couple collaborators, especially Amy Childress, my colleague who helped with the reverse osmosis stuff. And of course, thanks to the utilities for water and the government for money. Thanks.
Thank you, Dan. That was great. There's lots of things about wastewater. I will turn it over to the audience to see if anybody has any questions.
I have a question, Ashley.
Go for it, Joe.
That was a great talk. What water do you drink?
I get that question a lot. I drink normal LA tap water, and I'm not too worried about it. You know, it's a funny thing working in this area, because on the one hand, we want to communicate confidence to the public, right? That your tap water is good to drink. On the other hand, we're studying contaminants in tap water all the time. So how do we square that circle? In my head, it's that, you know, the level at which we're worried about a contaminant is somewhere between the 1 in 10,000 and 1 in 1 million cancer risk level. And so on a population basis, that's worth worrying about, right? We could prevent potentially thousands of cancers by fixing some of these problems. But at an individual risk level, I'm not too worried about it. You know, like if there's chloropicrin in my drinking water and that gives me a 1 in 100,000 chance of developing bladder cancer during my life, I'm not going to lose sleep over that. So yeah, I just drink tap water.
I'm just worried that you haven't found some of the other ones that are maybe lurking in the water. I mean, you've targeted your analysis to one chemical, I think, or one class of chemical, and I wonder if there's other things lurking in our water, especially in LA.
Yeah, I mean, that's a big topic of discussion right now, not just in academia, but also at the EPA and other, regulatory agencies around the world. What do we not know about, and is it toxic or not? And I'd say there's two main lines of research going after that right now. Obviously, there's a lot of non-target mass spectrometry people can do to try to identify whatever we're missing with our targeted methods. And then the second one is there's been some renewed interest in the last few years on using bioassays to assess potential toxicity in water because, the bioassay doesn't care what the chemical's called or what its molecular weight is. It's going to say that something's toxic or not. Those are tricky, though, because to get a signal on a bioassay, you probably have to massively concentrate the water sample to go from a 1 in 100,000 risk of cancer to 1 in however number or whatever number of like fish or whatever you're going to test them with. Even if it's cells and you're doing high throughput stuff with, however many well plates they have these days, it's still probably going to take a concentration step. So, it's something people are actively working on, and we'll see where it's headed.
Yeah.
I wouldn't be too surprised if a bioassay appears in a future water regulation at some point, but I suspect it's going to be many years before that's really dialed in.
Good, thanks.
To bring this back to mass spec, Dan, you mentioned non-targeted mass spec is one of the assays to study this. Do you think that the current technology that mass spec offers is sensitive enough? What is the kind of difficulties when going after those non-targeted assays? Is it informatics? Is it?
Yeah, I would say, I mean, from my perspective, it's making sense of the data. I've dipped my toe into non-target stuff here and there, but it's definitely not my main line of research. And in part, it's just because it's so daunting dealing with all that data, I mean, I have good colleagues in other schools who do non-target as their bread and butter. And I just see what these guys have to do to come up with an answer. And it's so much work. It'll be like one student's entire PhD to like figure out one chemical that is causing some effect that they, picked up a signal from on the non-target. So yeah, it's a really cool tool. And we do lots of high-res mass spec for sort of semi-targeted stuff where we kind of know what we're looking for. But yeah, to me personally, it's just my opinion, but I think, just the massive information coming off of each of those injections is the hurdle to me right now.
Correlating that to something biologically relevant.
Exactly, yeah.
And
there's been some interesting progress in that in the last couple of years in my field. I was just at a Gordon conference last year, and I guess it's Gordon conference. I'm probably not supposed to share too many details, but because those talks are all off the record. But people are starting to do things now, like try to figure out if they can develop a chemical reaction that will sort of simulate or pick up on functional groups that are toxic, meaning like, okay, if you know that some certain class of contaminants reacts with XYZ biomolecule, or maybe even at the functional group level, right? Like it's going to react with a thiol on some protein and then do something bad to you. Can we just apply a thiol that looks like the business end of that protein to a sample, and then anything that reacts with, we suspect maybe is toxic. And then based on the mass of that probe that you've added, maybe we can do a somewhat more targeted high-res mass spec to try to figure out what compounds were reacting with that sort of simulated toxicity probe. It's still very early on, and none of that stuff's perfect yet, but I think that's a promising direction.
it's really interesting. Turn it back over. Does anybody else in the audience have any questions for Dan? All right. Well, thank you so much, Dan. That was a really, really good talk. And I know that it wasn't as mass spec heavy as we typically go, but it was really interesting to see how it all clicks together. And as you said, the mass spec's kind of going on in the background to advise of all of these. So thought it was really, really interesting.
Cool, thanks.
All right. It is now the time in the evening. I'm going to turn this over to Dr. Mark Strynar. He is a senior physical scientist in the Center for Environmental Measurements and Modeling within the Office of Research and Development at the US EPA. His research interests include high resolution mass spectrometry to investigate the fate and transport of per and polyfluorinated compounds, or PFAS, and other xenobiotic compounds in biological and environmental media. Additionally, he is interested in novel compound discovery and environmental media and development of analytical methods for unique biomarkers of exposures to chemicals that are useful for toxicology or human epidemiological studies. So this is a really nice transition from the conversation we just had with Dan to Mark. So I'll hand it over to you, Mark.
Okay, I will also need you to tell me whether or not I'm full screen or if you see what's coming up on the slides.
Looks
You are
great.
full screen.
You'll
Great. Well, I thank Dan for doing the heavy lifting to sort of start a bunch of the conversations about, water quality. And you can see who I work for, the United States Environmental Protection Agency. And I work for the organization that's the research and development wing. I do not work for the regulatory wing, but many of the things that Dan talked about are important because we are to protect water quality and we're to protect air quality. And so, for example, the laws that govern our nation with clean water, the Clean Water Act, for example, has a permitting process. In particular, things that are permitted to be released into the environment by industrial sites and other locations. And I do mainly non-targeted analysis and looking for what is coming out of industrial sites in support of my agency's law enforcement wing, which is kind of funny. I talk to more lawyers now than I do to chemists. I'm going to tell you a lot about mass spectrometry, but you should know that in our nation, an NPDES discharge permit, that's the non-pollution discharge elimination system, is making you not put things into the environment that you're not permitted to do so. And if you do put something in, it's a violation of that law. So I help our lawyers keep industrial polluters sort of in check. And I'm specifically going to talk about PFAS, though I work on many other things. And maybe I'll mention a few as we go. On behalf of my colleagues, James and Jackie, I'm going to give this talk. So I want to start off with probably what Dan led off with. Ignorance is not bliss, because if there's a compound out there we don't know about, we can do nothing about it. We can't remediate it. We can't get rid of it in an advanced oxidation system if it's in drinking water. And so my job is to find the things that are out there so that my organization can make a determination, and other people that care about water quality can make a determination about what we can do in this situation. And I try to explain it as, the home that you live in is built upon a foundation. I don't know where you live, but depending on where you live, it could be a slab, it could be a poured foundation, it could be on pylons. But that foundation is critical because the structure stands on that. And if that's wobbly and it sinks in and moves left to right, then your house is not as good. So compound identification and the work that I do is the foundation of all the rest of the work that goes into what my agency does, and other people on this call probably do. When you look at occurrence, non-targeted analysis allows us to see those things that are invisible to the usual person doing targeted work, which I'll talk about later. Once you know about a compound, you can then do a risk assessment of it. Maybe you have some biological data. Maybe you've done a bioassay. If you don't have that, the chemical is not known to you, you can't do that. And then remediation, cleaning up the contamination. There are many, many more things that still require that compound to be identified. And so I show that as the basis. So I would claim that high resolution mass spec is a key to how we do this work. And I'm going to get a little bit into that. That's the job that I do. Do I do low resolution mass spec work? I do a lot of high res work. So if you're not familiar with these terms, low resolution mass spectrometry, like a triple quad with a targeted method, could answer the question, how much PFOA is in my water? It's much like shooting at a target. So you're having a list of compounds that you're looking for on your mass spec. It's a validated method. You've got a calibration curve, and you're trying to give an estimate of concentration based on the extract you get. So non-targeted analysis is broken into two groups. So sometimes it's called untargeted, where you don't know what you're looking for, and you could ask the question, what chemicals are in my water? It's more like casting a net, and you're trying to see what you catch under that net. And it's further broken into two groups, which I'd call suspect screening. So there's a database somewhere. It could be NIST. It could be the EPA's Comtox dashboard. It could be something you bought with your vendor software, where you're looking for those chemicals in your sample based on the database that you purchased. I also do non-targeted analysis where I'm simply trying to figure out compounds that are present that are not already on lists, that if I can get to the bottom of what they are, we can begin to make the rest of the decisions about remediation, risk, et cetera. And this I would term environmental forensics. We're really doing work to figure out some of the questions earlier on, the unknown things that are present in the water. And I think this is really a fun job. It's daunting, as it was mentioned, but it definitely keeps us on our toes. So how do I do this? This is a picture of me on the Cape Fear River. If this is a source, if this is an industrial source that has a pipe going into the river, you should also see it has an air source. So air people can do the same thing. But the discharge into the river, we're trying to ask the question, what is in the river coming from that source? And it's hard to do because industrial rivers can have non-point sources like a farm where overland runoff happens, biosolids application, pesticides, nutrients whatsoever. They commingle. It could also be that there's a golf course that has non-point source, pesticides, again, nutrients. And you're trying to get to the bottom of what is in that river that's coming from the industrial polluter. Along the same lines, it's an industrial river with a mishmash of things that are upstream and downstream. And so you can understand the complications here in trying to figure out who the potential source is of the compounds. So taking samples with time and space and looking at all the samples you receive and drawing a conclusion is often the way we go about our work. And we work with a lot of program offices. A week I mentioned the law enforcement wing. And then because we're federal, we have a lot of states and a lot of regions that want to know how to do what we do and help them figuring out these industrial sources, what's being put into the river. And one of the tools we use is this negative mass defect. And I talk to a lot of people who are not chemists, so maybe this is second nature to you, but with organic compounds made up of carbon as the backbone, carbon is what we call mass neutral, 12.0000, okay? So if you have a big long stack of carbon and you put hydrogens on it or nitrogens on it, that imparts a positive mass defect. It's slightly more than a whole number is a better way to put it. And the rest of these elements that I show you here, from oxygen on over to iodine, impart a negative mass defect. So it's less than a whole number. And what I hope you can see is the degree of that defect is dependent on the element that's added. I work on polyfluorinated compounds. So usually carbon, oxygen, hydrogen, a lot of fluorine. They're perfluorinated or polyfluorinated. They don't add a whole lot of negative mass defect, but they tend to be highly fluorinated. And so I want you to see it's almost 5 fluorines that are required to overcome the positive mass defect of a proton. So polyfluorinated compounds fluctuate slightly above positive mass defect and certainly below can give you a negative mass defect. And I'll give you a few examples. So here's a compound in our body, octanoic acid, fully hydrogenated with a carboxylic acid at the end. All the hydrogens have a positive defect. Carbon is mass neutral, 12.0000, and it has 2 oxygens on it, okay? This has a positive mass defect, slightly more than a whole number, and it's naturally occurring in our bodies. If you fully fluorinate that compound to make PFOA, perfluorooctanoic acid, all of these fluorines being added on, yes, they make the molecular weight much larger, because fluorine is 19, hydrogen is 1, but it also gives it a negative mass defect. And that is a characteristic of PFAS that is a phenomenal thing to look for and find, because degradation products and metabolites and fragments all have that same negative mass defect. And I sometimes talk to people that don't even know elements. So I put up my wife's favorite example of her favorite element, carbon, because she loves this gemstone on the bottom, diamonds. So how do we put this into practice? This is an example from an effluent stream. This is near a facility we published on the Cape Fear River. Over here on the far left is the mass defect. So anything above this line has a positive mass defect. Anything below the line has a negative mass defect. And then you can see the effluent is in red and the upstream sample or the receiving water body is in blue. So this oval that I've sort of called out in this area is high priority because they're both unique to the downstream sample and they're likely fluorinated because they have negative mass defect. So the daunting thing with high res is you get a lot of data and you're trying to whittle down what it is to work on. And we did go and look at what was found in these samples and published a paper where we first discovered Gen X in the Cape Fear River. So how do we normally do our work? We normally take our sample and we run it through solid phase extraction. Here we use weak anion exchange. We have an Agilent 6546 QTOF where we're doing some data dependent acquisition. So we're getting MSMS at 3 different voltages. We do peak picking with the OEM software. It's called ProFinder. That's the Agilent version. Because we do a lot of work on fluorinated species, we've started using this product. It's actually free to you. It's called FluoroMatch. There's a reference you can look at. Jeremy Colmel wrote it in 2020 and 2022. This allows you to go through that peak picking features, which is a retention time, a molecular weight, and an abundance, match it against known PFAS, and then I'm going to show you the output later. And then last, manual annotation. This takes a ton of time when you find things that are not in the software, that are not in the database, and you're trying to get to the bottom of what they are. We also have a thermo Orbitrap Fusion, which does very similar work. It just does different workflows in order to get to the end. And it's asking the question from among the shotgun, which is very typical, thousands of features. What do I need to worry about? What's fluorinated? What's toxic? What do we need to remediate? And that's the daunting thing about this work. So I'll tell you a little bit about a new piece of equipment in my lab. This is sort of the normal. We have an LC sample. We prepare it. We get chromatographic separation. It goes into the ion source where we can get MSMS. Here, this would be our quadrupole time of flight, our Orbitrap detected. And we spend a ton of time looking at data for processing and acquisition. We recently got a high resolution ion mobility system into our lab based on the work of me and Mobile Ion Systems. I know some of our colleagues are on this call today. And it's a new thing in my lab because it now allows us to take ion mobility, putting it in front of the detector, the quadrupole time of flight, and after the source, and putting a new degree of separation. And so I give one example here where I took a PFAS standard. So prior to being able to buy PFAS years ago, 3M would give it to us. They called it Lot 217. It's a mixture of branched and linear isomers. Those isomers can be separated chromatographically if you do a very long run. I'm showing you here what's called the ballistic gradient, which is less than 3 minutes. It's an extremely rapid ramp up to 100% methanol. The compound really comes off in less than a minute. And then what you can see here is the new dimension. It's this arrival time. So you have arrival time and you have mass spec, and you get these nice heat maps where you can clearly see that there are multiple isomers showing up. So I'm just beginning to start to use this thing and make data, share it with our colleagues at Mobile Ion Systems, and putting in an abstract. Hopefully we're going to present at ASMS. This is with no column. You can see here there's really no difference between the ballistic gradient and the no column. You can also use your standard gradient and have massive separation as usual. But here's the theory behind this if you don't know about it. For example, here, we're looking at far over here to the left. These are the ions, the compounds that are present in the sample, going through the funnel to be focused. They come into the slim board. So this is unique to Mobile Ion Systems where they're caught at this gate. And when you allow them to go through the gate, they move through the slim board and they separate based on their mobility. Okay, so as they arrive at the end at the QTOF, what I want you to see is this is a 1 second time to get through the slim board. It's 150 microseconds where the quadrupole time of flight is firing. That's 6,666 times it can happen in that 1 second. So you get a lot of slices across those compounds coming out rather than not having the ion mobility. All the ions would automatically jet directly to the QTOF. And while it's going on, the ions that you're not collecting, rather than sending to the slim board, get jetted to waste. So it's a new opportunity for me to play around. I don't have any more to show you on that. I just wanted to tease you with some of the things we're going to start looking at. So here's what our data typically looks like when we use a non-targeted analysis on our QTOF ProFinder alignment, and once it's run through FluoroMatch. You can go look up more about this, but you have to visualize this data through this visualizer, which is powered by Microsoft Power BI. It's a Microsoft product. A lot of people don't have on their instrument, but you can install it. It looks again at the mass to charge, retention time, and area, and it matches against fluorinated compounds. But I think I'm going to show you examples. I hope you understand. Polyfluorinated compounds are usually homologous series, so they're repeating units. In this example, I say a CF2. Every time you add a CF2, it just grows in length. And so it also allows you to take compounds that are together as a unit. They're a homologous series, which helps us to figure out one, we can figure out maybe 6, 8, 10. And I want to give you an example in the slides to come. You can also change the repeating unit. It doesn't have to be CF2. For polyfluoros, you can do CF2O, you can do C2F4O, you can do lots of different things. I'll show you a few examples. So, and this example is from an industrial site. I'm circling a PFAS homolog. So if you don't know PFAS, PFOS is the 8 carbon chain link sulfonic acid. And what I want you to see is when you do this fluoromatch matching in the CF2 grouping, they fall on a horizontal line. That's because of calculations of Kendrick mass defect. And that's important because sometimes we don't know what the homologous series is. The examples I'll show you in the future. It's nice to see, however, that the ones that we're already aware of gives a formula, gives a SMILES notation, gives a name. So in the next example, this is an industrial producer where we saw that there were 3 compounds that were showing up on a horizontal line. So we knew they were associated with each other. The software was aware of 2 of them. These are the 2 it knew. So it's got this central nitrogen in the middle that's charged, sulfate on either side, and a perfluoro wing on either side. But it didn't know the top one. We, however, knew this top one because of some work we were doing. This is known as bistriflamide. So this is a lithium-ion battery ionic fluid, commonly found in the batteries in our rechargeable devices like our computers, our phones, our Apple Watches, etc. And the one that we're looking at here, this is the brand name from 3M. It's called HQ115. This has actually been looked at the EPA, and I think an MCL has been derived for or something similar to that. But we were able to put them into a pile and at least understand 2 that the software knew, 1 that we knew, and now we can report back to Fluoromatch. Jeremy put this in there so everybody else in the world, when they see this molecular weight and they see the spectrum, can figure out what it is. So here's another example of industrial producers. This is classically where I spend most of my time looking at their effluent. Are they or are they not putting something in the river they're not allowed to? Again, I have a homologous series on a flat line. You can see the molecular weights. Classically, they differ by 50. CF2, CF2, CF2 is 50 each time. It's actually 49.9898. But what we found in this group was that this compound was present. So it's a nitro in the middle, carboxylic acid. We have the MS data showing the spectra that we get. We can confirm that it's this molecule, and the homologous series that's on either side of it, smaller and bigger in size, were also present, and they differed in retention time. So none of these had SMILES notations. None of these had formulas or names. So at least we're to the point now where we can say we're fairly confident in this. Need a standard to confirm it. Okay. Another example at an industrial site, not in our blank, which is always important because PFAS sometimes show up in blanks. But it was in the sample, it was a staggering high level. And what we tend to see with PFAS that are really, really concentrated, carboxylic acids, phosphonic acids, sulfonic acids, they dimerize in the gas phase. There's competition in the source for other ions. And so this is the compound as a dimer in the gas phase, as a trimer, as a tetramer. But it's still all pointing back to the original molecule. We got MS on this. We saw these fragments. And these fragments turn out to be, get my face out of the way, this compound, which has a phosphate on the end. It's got HFPO-derived center. And then each of the fragments you can see here on the MS spectra, High Resolution Mass Spectrometry, confirming that these fragments are what we think they are, back predicting formulas. We can find this molecule in SciFinder, and I want to show you, just stare at that structure. It's real similar in structure to GenX or HFPO dimer acid. We anticipate that this molecule could undergo oxidation. We could cleave this ester, turn it into an alcohol, and likely turn it into a carboxylic acid through further oxidation. Maybe some other chemical oxidation as well, I don't know. But this is a new one to us, and we have found this in an industrial site in their effluent. Okay, another example is we see a lot of isomers, and a lot of people, look for the one compound they're interested in, but they don't really look that there are others. In this example, over here on the far left in the orange, this is actually HFPO dimer acid or GenX. This carboxylic acid falls off readily in the source. So the orange trace is the decarboxylated trace. The red trace is the intact molecule that has the molecular weight 328.9. What I want you to see is that there's this other isomer right next to it with the same molecular weight that does not decarboxylate. It actually fragments way down here near this ether bond to give this 184 fragment. And if you don't look for multiple isomers through high resolution, you would completely miss the second isomer, which was actually higher in concentration. I normalized it so you could see them both. At this industrial site, they were making both a linear and a branched version of the same C6F11O3. Okay, if you're not familiar with hexafluoropropylene oxide, I'm going to talk about some NMERs, and I'm nearing the end of this. I don't know time-wise if I'm doing good. At an industrial producer, if you take this molecule, HFPO, and you dimerize it, you make HFPO dimer acid. Many people call Gen X now. Okay, you can see the structure here. This is the spectra that you get, fragment spectra for that molecule. But what we found at this site is if you dimerize it, you also trimerize it, tetramerize it, pentamerize it. And I don't know, I had to go and look up, once you get out here, dodeca. And I now know, in looking at the patent literature, that actually you can create anywhere from 0 to 25 subunits of HFPO. These are lubricants, they can be greases, and they can be oils based on the molecular weight of how many of those NMERs, oligomers you have present of HFPO. They're high vacuum oils and greases and things like that. We could see these without a doubt in there. I mean, as a mass spec person, I start to geek out when I see these spectra and I start to figure out what the fragments are and how they're related to each other. That in itself is a paper, but we found these in some industrial effluent. Okay. I know Dan talked about the chlorinated forms of the compounds, the halomethanes. I know there's iodinated ones, and I've read a couple of pubs on them. I got an interest in iodine because I had talked with Susan Richardson, and she said, you know, why do you only look at fluorine and chlorine and bromine? You're skipping iodine. So I looked in some samples, and I could see some iodine peaks, and it's a very unique element. It weighs a lot, 126.9045. And what I noticed is I had a lot of different retention times. Iodine is a great living group for polyfluorinated compounds. It's used in their manufacture. The iodine comes off quite easily, and you can replace it with other things. So I ran my mass spec. I looked for iodine being present. I found all these different molecular weights that they were coming from. I stacked them up, and I saw that there was a series of compounds differing by 50 AMU, and we proposed that they are these perfluorinated carboxylic acids with an iodine on the end. Seems to be supported by the literature we read, and seems to be supported by the industrial synthetic chemists we recently hired to help us make things. But the key here was finding that iodine was present and leaving those compounds in the mass spec source. The only fragment we got from this molecule when we did MSMS was the loss of an iodine. So it wasn't really all that exciting. Okay. And the last two examples I'm going to give you are about some other fluoropolymers. Okay. Tetrafluoroethylene on the far left is used to make polytetrafluoroethylene, many of us know as Teflon. So every carbon is fully fluorinated. This is an extremely strong bond. I didn't say that earlier, I'm sorry. This is great stuff. It does a fantastic job for the job it's intended to do. The dilemma is it's long-lived, and a lot of the things that are used to make it are what we see in our environment. Second only to PTFE or Teflon is this compound, PVDF, where every other carbon is fluorinated, every other carbon is hydrogenated. And so here are some of the trade names, Kynar, Hylar, and Solef, depending on who it is that's making that polymer. And what happens is when you make this polymer, you also make a lot of intermediates and low molecular weight compounds that are generated during the production of these PVDF polymers. And here's some work from my colleague, James McCurry. We're working on a publication on this. I show you some examples of those repeating CH2CF2 units with sulfates on the end or carboxylic acids on the end. I don't know if we have them here. Sometimes we see a sulfate and a carboxylic acid, a sulfonate, etc. And they're coming from the generation and creation of the PVDF as byproducts of the manufacturing process and being emitted into the environment. knowing nothing about their toxicology, knowing nothing about, do they degrade or do they not degrade, or do they bioaccumulate? But we are aware of these at one industrial site and are looking further into that. So that was my last slide. I put my contact information up there if you want to hit me up later for questions, but I can jump back in to any questions we might have from people that are on the line. I'll stop there. Hopefully I stayed close to on time. Or maybe I didn't.
Great, Mark. Before I ask questions, does anybody else have a question that's on the line?
I have a quick one if you got a second.
I'm ready.
So just out of curiosity, that iodine stuff you showed right at the end that came from maybe talking to Susan Richardson, do you have a sense, are the iodinated PFAS compounds there because the iodine conveys some kind of useful property, or is it just camouflage for the PFAS?
No, it conveys an extremely useful property. That iodine is easily taken off the end of that molecule and replaced with a whole bunch of other things. And then I get out into the realm of what I don't know about. My synthetic chemist, and looking at the patent literature, said it's super common, in particular at the sites we're looking at, for that iodine intermediates to occur, because they want to do something else to that molecule, take the iodine off, oxidize it, put an alcohol there, put a nitrogen, etc. So it is there for a reason.
Cool, thanks.
I had a question.
Sure.
Mark, you said it really quickly, and I had heard this before, but you said that there's PFAS in blanks. How big of a problem is that, and where is it coming from?
Oh, it's coming from everywhere. When I first started doing this job, everything you touch in the lab was suspect. The solvents you get, if you ever take the cap off of a 4-liter jug, it's got a PTFE lining. The HPLC vials you use have a PTFE lining. Many of the components in our LC and GC systems are fluoropolymers because they're considered inert and they do their job. The lines going down into your solvent, I can go on and on. Pipette tips used to be made with PFCs, PFAS, because they make them no stick to small volumes of serum. So anywhere and everywhere, and I have struggled with all of them.
So what do you do then? So you had a blank that looked pretty blank, but I don't know how hard it was to get
the biggest thing you can do is you can make yourself aware of all the components that go into your method, and you can test everything, and you can don't use the things that are really high in PFAS. Sometimes that's impossible. Once you get to doing analytical work, it's a trick we did probably about 15 years ago. There's something called a hold-up column. On the backside of your LC system, you're pumping the A and the B. And if PFAS are coming from the system, you can hold them up on a second column. And as you run your gradient, you have a physical separation in between your injector and your analytical column. Your gradient runs and you'll get 2 peaks. So the best thing to do is minimize through what you purchase and just watching your blanks on a regular basis to keep it as low as possible. But analytically, you can also deal with it by that hold-up column. A lot of people do that, or retrofit their whole system, get rid of as much fluoropolymers as they can. Sometimes you can't, the HDP lines, or instead of Teflon, use PEEK. There's lots of tricks.
I had another mass spec question. So all of your work was negative ion electrospray, and I wondered whether, GCMS would probably not work because your molecules are too big. Most of the PFAS stuff is, but have you considered other ionization methods like any of the DESI methods or any of the other ones that are out there?
I focus mainly on the negative ESI because 90% of my work is done there. We do have positive ESI because there are some polyfluorinated compounds like the ones that are used in aqueous film-forming foam. We sometimes call that AFFF to put out jet fuel fires, military bases and airports, fire stations. Those show up in positive mode. There are some other polyfluorinated compounds you can see in positive mode. So just on the LC end, between ESI negative and ESI positive, we get great coverage. We're doing volatile work now on a GC Orbitrap, where we're doing, my colleague Hannah Libertor is doing this at the EPA, headspace analysis, where they're then just taking the sample of water, warming it up, stirring it, and then whatever's in the headspace, taking it out, I think it's ESI. I'm not entirely sure, but
Mhm.
there's other people doing different you know, source methods that I'm not aware of, but I don't do it.
Good, thanks.
Got enough to look at already.
Mhm.
Good question.
All right, Mark. So what do you think the biggest challenge? What is your biggest challenge? Because obviously you have PFAS and everything. You're looking at samples that are sometimes difficult to work with. They're low level. You have isomers. Um, what is your biggest analytical challenge that you face, and like, do you have insights for how to address it if it isn't something we've already covered?
Yeah, I don't know if it's an analytical challenge. There's not enough time in the day is usually my answer. I think, distilling down when you get high res data, you have such a giant pile is trying to parse out what do we already know, compounds that are already on a database where we can cut those off the slice of the pie and make that slice, okay, don't spend any more time on that. And then spending as little time as possible doing the automated digging through the data. We've gotten a lot better in the last 3 years. And then the manual annotation, that's my biggest hurdle. A lot of the things I look at, unfortunately, are not in the databases that we're sleuthing. We set those aside and just sitting there with other chemists and trying to figure out first principles of chemistry. What is it we're looking at based on formula prediction and fragments? So my biggest challenge is like time of day.
Yeah, there's so many softwares I feel like out there, and this is definitely an emerging field. So, well, does anybody else on the line have a question for either Dan or Mark before I let everybody go? I know it's late by Mark, getting late here. Well, I want to thank you both for giving us a presentation today for LAMMS. It's been fantastic. I was really excited. This is a really nice inaugural talk. And thank you. If anybody has any questions for either speaker, please reach out to lams.dg@gmail.com and we can get you in touch with them in case you missed their emails prior. And if you know anybody that would like to do this, we're also we're doing 3 more of these this year. So please reach out to me and let me know.
Cool.
All right. Thank you, everybody. Have a good evening.
Nice.
Nice job.
Bye.
Bye-bye.